Hi there, my name is Dmitry and I welcome you on my technical channel. Today we are going to talk about prototyping boards and more specifically SolidSwitch Click, which in essence is a solid-state switch driven by I2C. This is the board. It looks nice and clean and small, but let's see what it can do and what it can't. We are going to interface it with the Arty Z7 board. So at first we would need to look at the project and hardware configuration of the Arty Z7. Let's do it. Let's have a look at the hardware configuration first. What I did, I enabled I2C interface on J2 for my board, and that created external interface connected to AXI I2C IP core. Please pay attention that it is not standard hardware block, which is part of the PS processing system. It has nothing to do with I2C interface. Which is already available as part of peripherals. So I2C 0, I2C 1 are disabled, as you can see. We can look at them here as well. I2C 0, I2C 1 disabled. Why is it so? Well, this is because of the physical pins connected to PL pins. So pretty much those pins are PL pins, and then there is no way to interface those pins with I2C 0 and I2C 1 peripherals. This is why it is a separate block which is implemented on PL or on FPGA side. It is connected through an AXI interface. This is why we automatically need AXI interconnect, and this is why we need to have processor system reset. I2C interface is made external. You can see there is ACL-I, well, three actually lines per each signal, ACL and SDA. Looking at the top level design, this is what we have: shield, I2C, SDL and SDA and ACL, and we also have signals coming out from the board design. These are the signals that we just saw right here. Now we need to instantiate I/O buffer, 2 I/O buffers, to interface with the external pins. And now the actual physical connection, the actual physical pin, or rather 2 pins, defined here SDA IO, and SCL IO again. This is the output of IO buff. This is the output of IO buff. And we are looking at physical pins 16, P15. P15, P16. This is what we need to know about hardware configuration. Now let's go to the SDK. First of all, we implemented a simplified I2C driver that does only two things, reads and writes. Well, it initializes the configuration, obviously, but this is tightly bundled with the actual board support driver, which comes from Xilinx as soon as we enable AXI I2C block. So in essence, in order to hide all this complexity, we implemented a simple driver that has two functions, I2C read, I2C write. On top of that, we implemented a mapper, which is I2C slave specific implementation. 70, in our case it is max 7323, and then we implemented just two functions again, to read and write. Slave address is defined here. We potentially have two addresses. We also define structure in order to be able to access those bits independently. And what we do, we initialize I2C interface, then we instantiate a variable of the max 7323 structure, set it to 0, and then we write that value to max 7323 using default address 68. That is in essence the application on Arty Z7. But let's do a hardware connection between the two boards. This is how I connected the two boards. So basically there is an LED connected through 180 ohms resistor, which is supposed to be controlled by, if we look at this schematic, which is supposed to be controlled by Vout 7. Vin I connected to 3.3 volts. So in essence I connected it with VCC. Now if we go to the Arty Z7 pinout, then there is SCL SDA signals, there is ground, and there is 3.3 volt rail. Let's switch camera. So this is the ice core C. SCL SDA. The green wire is ground. It goes into ground. The red one is VCC. It goes to 3.3. And at the same time it goes to V in. This is what we looked at just now. V in, let's double check. V in and VCC, yeah. So let's check the setup, whether we can get some results. So at this point our ice core C interface is not functioning, probably due to multiple issues. Could be on the software side, could be on electronical side. Let's try to hook up an oscilloscope and see if we can observe toggling signals on ice core C interface. We just armed oscilloscope and we're going to run our application and see if we can catch anything. Okay, let's do a single ice core C, right? Yeah, and we definitely can see something. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 clock signals, 9 clock pulses. And this is the first byte. It doesn't look right, but at the very least, we can see those two signal lines toggling, which is good, which means that our ice core C AXI ice core C module is functioning. It turned out that there is a problem with the reset pin. If we look at the module schematics, it doesn't go anywhere apart from reset pin, which means there is no either pull up or pull down resistor. Now if we look at the datasheet of MAX 7323, it says first of all that it is active low, and then secondly it is never mentioned that there is an internal pull up or pull down resistor. As a result, if we don't connect anything to that pin, it would automatically mean that MAX 7323 is going to be held in reset. So it is very strange because it is a good practice to make prototyping boards as convenient as it is possible, which is not the case obviously. Not only we need to pull this pin low, but we would also need to find additional pin somewhere, because we can't really easily connect multiple wires to just one single pin, which makes prototyping even more sophisticated. So what I did, I simply connected reset to 3.3 volt rail through 3K resistor, just to be on the safe side. So most likely our I2C interface is not functioning. This is why we connected the oscilloscope again, and we will try to understand what is going on signal level. So let's run the application. And step through the code. We're going to perform one single step, one single write to the I2C bus. So our oscilloscope captured something. Let's switch to a different view. So what we can see, there is 1, 2, 3, 4, 5, 6, 7, 8, 9 clocks, and only one byte, and the data doesn't look like the address we need to send, so it's definitely wrong. Now what I found is that for this driver we need to explicitly set slave address first. So it is like this. Then we obviously need to check and also do the same for I2C write. And let's see what happens now. Let's run it again. Switch to single capture mode. let's run again. Nothing happened, the oscilloscope didn't trigger for some reasons. Set address failed. Interesting. Of course. What kind of logic is this? First of all, it should be like this. Let's run again. Let's have a look again. So what we can see, nothing has changed in that sense. I found the problem. When we write, it should be send type. Let's run again. Arm, run. Okay, looks much better, so we can see the address now. But the number of bytes is still 1, which is not right, because we not only the protocol implies that address should be sent, there should be a data, 1 byte at least. And this is probably because we specify the number of bytes without taking into account address. So let's do it like this. Maybe it is how this type of driver works. Let's have a look. Let's run it again. Let's arm the scope and run again. So it looks so much better now. So we definitely send 2 bytes. The number of pulses doubled. The number of clock pulses doubled. And then looks like that we are sending 0. This is exactly correct. let's try to step through the second set of commands. Let me lower the camera to look at the LED. And let's try to do one more step. And the LED is working now. So our R2C interface is functional. If we do one more step, the LED should go off because we write in zeros again. Yeah, that's exactly what we wanted. So the board is finally working. What we have discovered in the process is that first of all, the reset pin should be pulled high. It's not very convenient to work with this board because it has only one 3.3 volt pin, and one more thing is that there are several not connected pins, which doesn't really explain why they can't be used as additional pins for 3.3 volts. Also, the address, the I2C address, can be changed by resoldering those resistors, which is also not very convenient. Instead, it could have been done with deep switches. Well, and all this comes at the price of $35 US. So they saved 10 cents on the resistor, didn't pull reset line high, they saved on deep switches, and then they didn't even route a 3.3 power rail to more than one pin. So it's up to you guys whether you're going to use this type of prototyping board or not, but for me it is probably no. Hopefully it was useful. Stay tuned and see you next time. Bye.